Hi, I'm Jada, and this is my presentation on neutron stars in merger ejecta. Introducing me. I am in 10th grade and I go to PTech. I love reading and listening to musicals. To the right are a few musicals that I enjoy listening to. The Roar program. I got into the Roar program through my school, and the Roar program is a program that teaches and introduces students to the study of astrophysics. And we are currently learning about neutron stars. Prior to the program, I knew nothing about coding or astrophysics. A little about a neutron star. A neutron star is full of particles called neutrons, and they can be created from supernovas. And it's only one result from a supernova because a supernova can create um, a neutron star or a black hole. When a large or massive star explodes and collapses, some particles combine, specifically protons and electrons, and they combine and create neutrons. And neutron stars can also create black holes by colliding and merging together. More about neutron stars. When two neutron stars collide and merge, they can have two different merger remnants. Those merger remnants are a heavy neutron star and a black hole. A heavy neutron star is very dense and would form earlier on. Centrifugal force and fast rotational speed keeps the neutron star from collapsing. A black hole would form later on, after the neutron star slows down and collapses on itself. Ejecta is the stuff that's ejected from the merger. There are two different types of ejecta, dynamical ejecta and wind ejecta. Both of these ejecta can create different elements such as gold and platinum. A dynamical ejecta is what's released within the first 10 to 100 milliseconds of the merger. There are two different ways to create or to form a dynamical ejecta. One way is for it to be thrown out, and another way is for it to settle into the disk surrounding the merger. Dynamical ejecta can make heavier elements than wind ejecta. And wind ejecta is what's thrown out after the first 10 to 100 milliseconds of the merger. To the right is a picture of the periodic table of elements. And this is a picture of dynamical ejecta from a simulation. Colors of light. Since ejecta is very hot and energetic, it releases light. Different color lights have different wavelengths. Light curves can help us study that different light. This is an example of light curves that we made. And it shows it shows different color light curves and how some light curves um, are brighter at the start of a merger, and some are brighter later on after the merger. So like the blue line is brighter early on, closer to between 1 and 2 days, and then later on it gets dimmer. And the red line is brighter later on, like closer to 4 and 8 days, and then it gets dimmer later on. Why I need to know how to code. Since objects we want to study are far away, we can't study them directly. So we have computer simulations to help us learn more about them. Code will help us analyze and read the different models that we work with. How I learned to code. I was introduced to Code Academy and slash Python, and I learned how to code by completing different lessons such as functions, lists, and loops. And we practice writing different codes on Google Colab. And to the right are an example of a function and a list. This is an example of a graph we work with in Google Colab. The point of making this graph was to see the differences between the orange line and the blue line. And those differences were that the orange line had more points and was more smushed together, and the blue line was more spread out and had less points. Um, that was because of the different inputs we put into the function. We made plots to determine which ejective parameter was most impactful on changing the shape of the light curve. And we also compared fast ejected light curves to slow ejected light curves. And these are examples of the ejecta parameters that we use: dynamical mass, dynamical velocity, wind mass, and wind velocity. These are plots for the the two ejective parameters, wind mass and dynamical mass. To the left is wind mass, and to the right is dynamical mass. And it's for the slow moving ejecta. So between, let's say, 1 and 16 days for wind mass, the maximum limit for wind mass has a bigger difference in a bigger peak than the minimum limit for it. And for dynamical mass, there's a difference, but it's not as big as the wind mass between 1 and 16 days. These are two other plots for the same two ejecta parameters, but this time is for fast moving ejecta. And there is like a big gap between the maximum and minimum limit of for wind mass. And let's say between 1 and 8 days, it's like a bigger gap. But for dynamical mass, between 1 and 8 days, there's not really a big gap. So there's not really a difference for dynamical mass than wind mass. So the conclusion we came up with was that wind ejecta had more of an effect on the light curve than dynamical ejecta. What we know about the lifetime of a merger. If there's a lot of ejecta, then there will be a long-lived big neutron star, which means that it can form into a heavy neutron star earlier on, and then a black hole later on. If there's a little ejecta, it will be a short-lived big neutron star, and it will form into a black hole earlier on. Future work. So we can compare theoretical models to telescope data. So models we make, we can compare it to telescope data and see how close they match. And we can adjust our model physics as we get more observations. So we can like change the assumptions of our models, like the shape of the ejecta. And this is a picture of different telescope data of light curves. Conclusion. I was introduced to Code Academy. I learned coding by completing lessons and practiced writing codes on Google Colab. I learned how to read and write data. We use graphs and plots. I learned about neutron star mergers slash ejecta, and I learned about light curves. And that is the end of my presentation.